Today, we're going to tackle a concept you probably think you know: infinity. But what if I told you that in the world of mathematics, it's a whole lot stranger and way more profound than you could possibly imagine?
All right, let's just dive right in with a question that honestly sounds like a complete riddle. Picture all the counting numbers in your head: one, two, three, four, just stretching on and on forever. And my question to you is, can you take that infinity and somehow make it even bigger?
It feels like a trick question, doesn't it? I mean, infinity is supposed to be the biggest thing, period. But this isn't some philosophical game. It is a profound mathematical truth. There isn't just one infinity. Oh no, there's a whole hierarchy of them. And getting our heads around this didn't just solve a puzzle. It completely revolutionized the very foundations of math. And we're about to see exactly how.
Now, to solve this mystery, we can't just count. I mean, how do you count something that never ever ends? We need a special tool, a whole new way of thinking about what the same size even means when we're dealing with infinite things.
And that tool is called one-to-one correspondence. It's a really beautiful, simple idea. Just forget counting. All you have to do is try to pair things up. You know, if you have a room full of people and a room full of chairs, and every single person can sit in exactly one chair with no chairs left empty, well, you know you have the same number of people and chairs, right? You don't even have to count them. This is the key we're going to use to unlock the secrets of infinity. So let's test this tool out. We've got two groups of numbers. First, all the counting numbers, 1, 2, 3, 4, and on and on. And second, just the even numbers, 2, 4, 6, 8. Now, your gut is probably screaming that there are more counting numbers, right? I mean, the even numbers are literally inside the set of all numbers. It feels like there should be half as many.
But what happens when we try to pair them up using our new tool? Okay, let's take the first counting number, 1, and pair it with the first even number, 2. We'll take 2 and pair it with 4, take 3, pair it with 6. You see the pattern here, right? For any counting number n, you can just pair it with 2n. Is there a single counting number that won't have a partner? Nope. Will there be any even number left over? Never. So what we have is a perfect one-to-one pairing. And according to our tool, that means these two sets have the exact same size. This is our first major clue that infinity just does not play by the normal rules. It's a world where a part can be the same size as the whole. Weird, right? Okay, now that our intuition has been totally shaken up, let's get to the main event. What happens when we compare the infinity we've just been looking at, this countable infinity of numbers, with a totally different, much denser kind of infinity? This puzzle was solved by a brilliant mathematician who was about to change our understanding of reality itself. So here it is, the big showdown. In one corner, we've got that countable infinity of natural numbers. We call them countable because you could, in theory, list them all out, one after another. And in the other corner, we have all the real numbers, every single possible decimal packed into that tiny little space between 0 and 1. I mean, think about that. 0.1, 0.5, 0.12345, pi divided by 10. It's a whole infinite ocean of numbers. So are these two infinities the same size? To figure this out, we're going to try to do the impossible. Let's just pretend for a second that we can make a complete list of every single number between 0 and 1. We'll number them. Here's the first number on our list, the second, the third, and so on. We're trying to pair them up with the natural numbers. If we can actually make this list, then the two sets have to be the same size. So here's our made-up list. Number 1 is 0.1415, number 2 is 0.73205, and so on down the line. Now, we are assuming this list is absolutely complete. It's got every single real number between 0 and 1 somewhere on it. Now look closely. I want you to pay very close attention to the digits running along the diagonal. Okay, here's the genius part. We're going to build a brand new number using that diagonal. For our new number's first digit, we'll just pick something different from the first digit of the first number on our list. So since that's a 1, let's pick 2. For the second digit, we'll pick something different from the second digit of the second number. That's a 3, so let's pick 4. You see what we're doing? We just keep repeating this process all the way down that infinite diagonal. And here it is. We've built a new number. Let's just call it D for diagonal. We know for a fact its first digit is 2, its second is 4, its third is 3, and so on, forever. It's definitely a real number, and it's definitely between 0 and 1. And now for the killer question. This new number D that we just created, is it anywhere on that list we made?
The one we assumed was totally complete?
The answer is a huge, resounding no. And just think about it. Could it be the first number on our list? Nope, because we deliberately made its first digit different. Could it be the second number? No way, its second digit is different. Could it be the millionth number on our list? Still no, because we made sure its millionth digit would be different. Our new number is guaranteed by its very construction to not be on the list, and this means our original assumption that we could even list all the real numbers was just wrong. It's impossible. There are more numbers between 0 and 1 than there are counting numbers. We've just found a bigger infinity.
This proof, well, it's absolutely mind-blowing. And it wasn't just some clever party trick. It fundamentally changed mathematics and our entire understanding of reality. And believe me, the story of the man who figured it out is just as dramatic as his discovery. This is Georg Cantor. Born in 1845, he was the detective who finally cracked the case of infinity. He developed a whole new branch of math we now call set theory, specifically so he could talk about and compare these different sizes of endlessness. But his ideas were so radical, so completely counterintuitive, that the mathematical establishment of his day pretty much reacted with fury. I mean, leading figures viciously attacked him, calling his work a grave disease, and labeling him a corrupter of youth. The pressure was just immense, and it contributed to severe bouts of depression that haunted Cantor for most of his life. But other mathematicians, like the hugely influential David Hilbert, they saw Cantor's genius. Hilbert realized that Cantor hadn't created a disease at all. He had created a paradise, a new, richer, and far stranger mathematical universe. He famously said, "No one will expel us from the paradise that Cantor has created." And you know what? He was right. Today, set theory is the very foundation of modern math. This all leads to a really fascinating final question. We've proven that these uncountable infinities exist, but where? Do they exist out there in the physical universe around us? This is a super important distinction. Mathematical existence is not the same as physical existence. See, when a mathematician says something exists, they mean it's a logically consistent idea. It's provable inside their system of rules. Whether there's a truly infinite number of points in a real physical line, well, that's a whole other question for the physicists. Cantor's infinities are real as concepts, as pure tools of logic, no matter what the physical universe is actually made of. And that's really what makes Cantor's work so incredibly powerful. It's a reminder that the universe of ideas can be just as vast and surprising as the physical one. It forces us to ask, if a concept that seems as simple as infinity can hold such strange, layered complexity, what other simple truths are just sitting there, waiting for us to unpack them and reveal a universe far richer and far weirder than we ever thought possible?